Welcome back. This is the third and final video recording from the lesson week 3 of IM2 distance learning. So now we're going to go into central angles, arcs, and sectors. To explore this, we're going to go to the link, GeoGebra link. And while we're doing so, you're going to be taking notes on what you think is the definition of central angle, arc, and sector. So here we go. Central angle is an angle made by two radii. That's the plural form of radius. So you have one radii here, CA, and BA is another radius. And then the angle that is formed by these two radii, this 44 degrees, will be considered the central angle. A sector is a pi-sliced portion of the circle. So in this case, it's this purple portion of the circle. And an arc is a portion of the circumference or the red curve. Okay, so if I was to move this point C, I can change the central angle from 78, 114, all the way to being very, very big, all the way to 360 in fact. Okay, and look at what happens to the length of the red line, the arc length. It changes according to the central angle. And the area of the shaded the sector area also changes as well. So I'll show you my definition of central angles, arcs, and sectors. If you need to modify your definition to make it more fuller, please add any additional information. So the central angle is an angle made up by two radii of a circle. Its vertex is at the circle center, point P, and it does not have to be always called P, it can be called any letter. But it's important that vertex of that angle is at the circle center. An arc is a portion of the circle's circumference. A sector is a pi slice of the circle. So it's the area between the two radii and the connected arc. So angle ACB is a central angle. But also if I was to do a reflex angle going from all the way from here to there, that would also be considered central angle. So knowing that, remember, central angle just means the vertex has to be at the center of the circle. In this figure, how many central angles do you see? See if you can count them and come up with an answer. Okay, so I actually counted 12. So let's see how I got that. So I count 1, 2, 3, 4. But each of these 4 angles, central angles, has reflex angles that goes with it. So with this 1, with this angle 2, with this angle 3, and with this angle 4. So, and then on top of that, I can connect 2 of the central angles together to form a new central angle. So that's 1, 2, 3, and then 4. So I actually count 12 central angles together. Now, the thing about central angles is that they always need to add up to 360 degrees. Why? Because that's the definition of full revolution. A full revolution is 360 degrees, so therefore 80 plus 110 plus x degrees need to add up to 360. So then you add those up and you get x to be 170 degrees. What's the measure of this? You are given 175 degrees here, 100 degrees here, then what's the third angle? Well, non-overlapping central angles in circle must add up to 360. So x is 85 degrees. Let's try this problem. Okay, so if you're given this central angle as 45 degrees, then what's this angle going to be? 45 degrees. Why? Because they are vertical angles and vertical angles are congruent. Then we can call those unknown angles x, and get the expression x plus 45 plus x plus 45 is 360, and simplify the equation and get x to be 135 degrees. This time I want you to try, even this picture, what is the unknown central angle? Please pause the video and solve it yourself. And here's the answer. X plus 180 plus 50 plus 90 is 360. Therefore, X is 40 degrees. Okay, how about this one? X plus 2x plus 90 plus 90 has to be 360 degrees. So we get 3x plus 180 degrees is 360, and therefore x has to be 60 degrees, and the other angle has to be 120 degrees. Okay, now we are going to watch a video.
Lesson on arc length and sector area. But first, let's just talk about circles. Every circle starts out with a center point and a radius. If we add those two basic things, we can loop that radius around 360 degrees and form a circle. And we know that the length of the outside of any circle is called its circumference, wherein any circle is equal to 2 pi times the length of the circle's radius. We also know that the space contained within the circle is called its area. For any circle, area is equal to pi times the radius squared, since we measure area in square units. Now, with those familiar circle properties in mind, let's go ahead and ask the question, what if we didn't want the whole circumference of a circle? What if we only wanted the length of a portion of it? In this case, we wanted the length of an arc AB. Now, if we know the length of the radius of the circle, and we also know the measure of the angle that intercepts the arc, in this case arc AB, we can use what's called the arc length formula to find the length of that arc AB.
Here's a quick explanation of how they got the formula for arc length. So let's just talk about whole circle circumference. That's 2 pi r. The whole circle is 2 pi r. But of that, we're interested in just the portion that is inscribed by this angle theta. So since I know that the whole revolution is 360 degrees, we have theta over 360 degree part of the whole circle. So the rate we have a theta over 360 portion of the whole circle here. So the arc length is going to be that portion we have, theta over 360 degree, multiplied by 2 pi r, which is the whole circle circumference. And then 2 and 360 here, they simplify to be just 180 as a denominator. And then bringing r to the top, that's theta times r divided by 180 times pi is the arc length formula.
Sector. Again, if I know the measure of the central angle within that sector and the length of the radius, I can use the sector area formula to find this area.
Let's also look at the sector area formula they talked about. How did they get that? Well, whole circle area is pi r squared, and of that whole circle, we have pi over 360, part of the whole circle. We're really talking about a portion of it. So the sector area is going to be pi divided by 360 times pi r squared. So that simplifies to pi times r squared divided by 360 degree multiplied by pi.
Now let's take a break for a second and talk about pizza. We can think of sector area like how much cheese would be needed to cover the surface of 2 slices of pizza, not the entire pie. And arc length is like finding the curved length of the crust on a few slices, not the entire pie. so let's go ahead and jump into our first example here. We have circle P shown below, and we know that the measure of angle KPL is 120 degrees. The diameter JL equals 24 centimeters long, and we want to find the length of arc KL. Now here's why you're going to use the arc length formula to answer this question. We want to find the length of KL, so we want to find that curved distance on the outside, not the area of the inside. So now to use that formula, I need two pieces of info. I need the measure of the central angle theta, and I need the length of the radius. That's going to be our R value. We already know that angle KPL equals 120 degrees. So that's our value for theta. We also know that the diameter is 24 centimeters long. Divide that by 2 gives us our radius of 12 centimeters. And now we are ready to substitute those values into the arc length formula. Replace theta with 120, replace R with 12, and then we can evaluate. So 120 times 12 equals 1440, and 1440 divided by 180 equals 8. Now in terms of pi, that arc length is just 8 pi. We can evaluate 8 pi to approximately 25.1 centimeters. That is the curved length of arc KL. So for our next example, we have circle K shown below. We know that line KC is a radius whose length is 5 centimeters long. We also know that angle AKC is 117 degrees, and we want to find the area of the green shaded region. Now we're going to be using sector area formula for this question because we want to find the area of one sector, one portion of the inside of that circle. So the information that we need is the measure of theta, the central angle within that sector, and we also need R, the length of the radius of the circle. We already were told that angle AKC has a measure of 117 degrees. However, that's not the angle that we want. But we should notice that angle AKB, the angle that we do want, is its supplement. So to find this angle, we do 180 minus 117, and we get 63 degrees for theta. And we were already told that line KC is a radius with a length of 5 centimeters, so our R value is going to be 5. The last thing we need to do is substitute. Replace theta with 63 and replace R with 5. And now we can evaluate 63 times 5 squared is the same as 63 times 25, which equals 1575. Then divide that by 360. This is equivalent to 35 pi over 8, or approximately 4.4 centimeters squared, the area of the sector shaded in green.
So what did we learn today? We learned to figure out the coordinates of any parabola even when a is not equal to 1. We learned about circumference formula and area formula and how we can use those formula to calculate circumference and area flexibly. We learned about central angles, what they are, and how they all add up to 360 always. And we learned about arc length. This is an arc, and if you are interested in finding the arc length, you can use the proportion of theta divided by 360 and then multiply that by the circumference formula or use this formula to find the arc length. And finally, the area of a sector or sector area can be found by dividing theta over 360 and then multiplying that by the total area, and therefore use this formula. So now if you were not here for this, the class did a quiz. So if you were absent from the lesson today, you need to contact Mrs. Van Horn ASAP so that you can arrange a time to take the quiz that everybody else took. So that's the lesson for today. I believe you should be able to do your homework now. Okay, thank you for watching. Take care.